If you've ever been to a construction site in South Africa, you've seen it. Steel everywhere. Steel rods stacked on the ground. Steel tied together in cages. Steel sticking out of concrete like it was forgotten there. Sometimes it's neat and organized. Sometimes it looks chaotic. And almost everyone has had the same thought at least once. Why is there so much steel? Isn't concrete strong enough? Why not just pour and be done with it? Some people even think that the steel is temporary, that it's there for alignment, or that it will be removed later. It won't. That steel is not a mistake. It is not extra, and it is definitely not optional. In this video, we're going to break down why steel is used in concrete, why concrete alone is not enough, and why that steel you keep seeing is doing far more work than most people realize, especially in South African buildings. To understand why, we need to clear up one very common misunderstanding first. Many people use the word cement when they're actually talking about concrete. You'll hear things like, the cement is cracking, they poured too much cement, this cement is weak. But cement is not the finished product. Cement is just one ingredient. Concrete is what you get when cement is mixed with stone, sand, and water. Cement on its own is like flour. Concrete is the bread. You wouldn't judge bread by tasting raw flour, and you can't judge concrete by thinking only about cement. When concrete hardens, it becomes very strong when it is being squeezed or pressed down. That's why concrete works so well under weight. That's why it's used for floors, foundations, bridges, and many other structures. But there's something concrete is very bad at. Concrete is weak when it is being pulled, bent, or stretched. And this is where many people get caught off guard. Structures are not just being pushed straight down all the time. Wind pushes them sideways. People move across floors. Cars move over bridges. The ground shifts slightly. Temperatures change. All of those things cause bending and pulling inside the concrete. Concrete can't handle that on its own. That's not a construction mistake. That's just how the material behaves. So when people say, why not just use stronger cement? The answer is simple. No matter how strong the cement is, concrete will still struggle when it's being pulled or bent. That weakness doesn't mean that concrete is bad. It just means that concrete needs help, and that help comes from steel. When concrete is squeezed, when weight pushes down on it, it performs extremely well. That's why you can stack weight on concrete and it doesn't complain. But the moment concrete is asked to stretch, bend, or hold something that wants to pull apart, it starts to struggle. And structures are constantly being asked to do exactly that. They bend slightly under their own weight. They flex when people move. They respond to wind, traffic, and temperature changes. These movements are often small, sometimes invisible, but they are always there. Concrete doesn't like that kind of movement. Steel does. Here's a simple way to feel the difference. If you clench your hands into fists and press them towards each other, it's hard to compress them much further. They resist being squeezed. That's concrete. Now imagine holding a pen, gripping one end tightly in each hand and trying to pull your hands apart. Without the pen, your hands separate easily. With the pen in place, they can't. The pen is doing the work of holding things together. That's steel. Steel behaves very differently to concrete. Where concrete cracks when it is pulled, steel stretches and holds on. Where concrete fails suddenly, steel gives warning. That difference is not accidental. It's the reason that steel is used. Steel is not there to make concrete stronger where it already performs well. Concrete does not need help being squeezed. Steel is there to deal with the forces concrete cannot handle. To picture this in another way, imagine a thick rubber eraser. If you press down on it, it resists quite well, but if you bend it, The bottom of the eraser wants to separate and open up. Now imagine pushing a wire through that eraser. When you press down, the eraser still does the work, but when you bend it, the wire prevents the bottom from separating. The eraser and the wire are not doing the same job. They are sharing the job. That is exactly what happens when steel is placed inside concrete. The concrete carries the squeezing forces. The steel carries the forces that try to pull the concrete apart. Together, they behave far better than either material on its own. This is why steel is placed inside the concrete, not next to it and not after the fact. Once concrete hardens around the steel, the two materials are forced to work together. They move together. They resist forces together. They fail far less easily together. This combination is not a shortcut. It is not an upgrade. It is the basic reason that modern structures can exist at all. Without steel, concrete structures would crack and fail far sooner than people expect. And without concrete, steel would be exposed, flexible, and impractical for most everyday construction. Steel and concrete are not competing materials, they are partners. Now that it's clear why steel is needed, the next thing people often wonder is this. Why does the steel look like that? Why is it round? Why is it ribbed? Why is it bent, tied, layered, and sometimes sticking out of concrete? This is where a lot of confusion starts. That steel is not thrown in randomly, and it's not there just in case. Steel is shaped and positioned very deliberately because of how forces move through concrete. Remember, steel's job is to deal with pulling and bending, so engineers place steel exactly where those pulling forces are expected to happen. That's why you often see steel closer to edges rather than in the middle. That's why it follows certain paths. That's why it's tied into cages instead of lying loose. Now, let's talk about something many people notice but don't fully understand: the ribs. If you zoom in closely on the steel used in construction, you'll see that it's not smooth. It has small raised ridges running along its length. That's what ribbed means. Those ribs are there for a very important reason. When concrete hardens, it grips onto those ribs. The ribs act like tiny hooks or teeth. Instead of the steel sliding inside of the concrete when forces act on it, the ribs lock the two together. This means when the concrete moves, the steel is forced to move with it. And when the steel resists pulling, the concrete is carried along with it. Without those ribs, the steel and concrete would not work as a single system. The tying wire people see on site is also misunderstood. It is not there to make the steel strong. It is not structural. Its job is simple: to hold the steel in the correct position while concrete is being poured. Once the concrete hardens, the wire becomes irrelevant. The steel and the concrete take over. You'll also notice steel sticking out of concrete sometimes. That's not because the job is unfinished. It's because the structure is being built in stages and the steel needs to continue into the next part so that forces can transfer properly. If steel stopped abruptly, the concrete would be forced to carry loads it is not good at carrying. So when you see steel exposed on a site, it's usually there on purpose. It's waiting to be connected. And this is important to understand. Steel only works properly when it is placed correctly, shaped correctly, and covered correctly by concrete. Too little steel is a problem, but so is steel in the wrong place. That's why steel isn't something you eyeball. It's not guesswork. It's doing a very specific job, one that concrete cannot do on its own. Once the concrete is poured and left to harden, something important happens that most people never see. The concrete doesn't just dry, it locks in. As it hardens, it grips onto the steel inside it, especially around those ribs we just spoke about. From that moment on, the steel and the concrete stop behaving like two separate materials. They become one system. When weight pushes down, the concrete takes the load. When bending or pulling happens, The steel quietly takes over. But here's the key thing to understand. This handover happens automatically. There are no switches, no moving parts, no human intervention. The materials respond naturally to the forces acting on them. You can think of it like two people carrying a heavy object together. One person is very strong when lifting straight up. The other is very strong at holding things together when they want to pull apart. They don't argue about who must work. Each does what they're best at. That's how reinforced concrete or concrete with steel works. When a structure bends slightly, and all structures do, the concrete on one side gets squeezed and the steel on the other side gets pulled. The concrete is happy being squeezed. The steel is happy being pulled. If either of them were alone, there would be a problem. Concrete alone would crack when pulled. Steel alone would bend too much and be impractical. Together, they balance each other out. This is why cracks don't mean that steel has failed. In fact, small cracks often appear because the steel is doing its job, holding things together instead of allowing sudden failure. This idea surprises many people. They think that cracks mean that something is wrong, but often cracks are a sign that the structure is responding in a controlled way instead of collapsing. The danger comes when steel is missing, badly placed, or poorly protected. Then concrete is forced to do a job that it was never meant to do. And that's when failures happen faster and more dramatically. This is also why reinforced concrete is used everywhere, from modest homes to massive bridges. Not because it looks strong, but because it behaves predictably. Many people see a crack in concrete and immediately think something has gone wrong. The steel didn't work, the concrete was weak, the builder messed up. But that's not always true. Concrete cracks. Even reinforced concrete cracks. That's not a defect. It's expected behavior. Remember, steel's job is not to stop cracks from ever forming. Its job is to control what happens after cracking begins. When concrete is being pulled or bent, tiny cracks form naturally. The steel then steps in and holds the cracked concrete together. Instead of one big, dangerous failure, you get small, controlled cracks. That difference matters. A structure with steel doesn't suddenly fall apart when a crack forms. It redistributes forces. It finds new balance. This is why you can sometimes see cracks in structures that are still perfectly safe. The problem is not the crack itself. The problem is what caused it and whether it keeps growing. If steel is present, if steel is correctly placed, and if steel is properly covered by concrete, cracks tend to stabilize. If steel is missing, wrongly placed, or exposed, cracks tend to widen and spread. That's when you start seeing other signs. Signs like sticking doors, walls that are separating, concrete breaking away instead of just cracking. This is also why painting over cracks or plastering them without understanding the cause doesn't solve anything. The structure doesn't forget what caused the crack in the first place. If the underlying forces are still there, the crack will return, sometimes right through the repair. So the real question is never just, is there a crack? The real question is the steel inside the concrete doing what it was meant to do? When it is, cracks are usually a warning sign, not a failure. When it isn't, cracks are often the beginning of a bigger problem. Up to now, everything we've spoken about assumes one important thing, that the steel is actually doing its job. But on many real construction sites, especially smaller or informal ones, that's where things start to go wrong. Not because people are careless and not because people are trying to do things badly, but because steel looks simple. It's just metal. It's just rods. It looks very forgiving. So people assume small changes won't matter. They bend it a bit differently. They move it slightly to make space. They leave it a little closer to the edge. They reduce some bars to save a little bit of money. And each decision seems small, But steel doesn't work on its own. Where it sits inside the concrete matters. How much concrete covers the steel matters. How far it continues into the next section matters. If steel is too close to the surface, it can rust over time. If it's not placed where the pulling forces actually happen, it can't do its job. If bars stop too early, forces have nowhere to move. From the outside, everything may still look fine, but inside, the system is already compromised. This is why two structures that look identical can behave very differently years later. One cracks slowly and then stabilizes. The other keeps cracking and it keeps getting worse. The difference is often hidden, buried inside the concrete. This is also why copying what you see on another site is risky. Steel layouts are not one size fits all. They depend on how much weight is involved, how far things span, what the ground is like, and how the structure is expected to behave. What worked next door might be wrong for your site. So when people ask, why do engineers make such a fuss about steel? The answer is simple, because once concrete is poured, there is no undo button. Steel mistakes don't always cause instant failure. They cause slow problems, and by the time those problems show on the surface, the steel is already locked in place. By now, it should be clear that steel in concrete is not about making things extra strong. It's about managing how structures behave over time. And this matters a lot in South Africa because many structures here are not built all at once. They are built in stages, over years, as money becomes available. A slab today, walls later, a roof much later, an extra story someday. Each stage adds weight. Each stage changes how the structure reacts. Each stage asks the steel inside the concrete to do more work. When steel is placed correctly from the start, the structure can adapt to these changes. It bends slightly where it should. It holds together when things shift. It gives warning before anything serious happens. But when steel is missing, when steel is reduced, or when steel is placed poorly, the structure has no safety net. Then small movements turn into visible cracks. Small cracks turn into growing cracks, and growing cracks can turn into disaster. This is why reinforced concrete is not just an engineering idea. It's a long-term decision. It's about choosing materials and details that forgive change, because change is guaranteed. Weather changes, ground conditions change, usage changes, family needs change. Steel is what allows concrete structures to survive all of that quietly without drama. So when you see steel on a construction site, it's not about overbuilding. It's about planning for the future, even when that future is uncertain. If there's one thing to take away from all of this, it's not that concrete is weak, and it's not that steel is there just in case. It's that modern structures work because different materials do different jobs, and they do them together. Concrete carries weight well. Steel holds things together when movement happens. One without the other leads to problems. That's why the steel you see on construction sites is not decoration, it's not temporary, and it's not optional. It's there because structures move, bend, settle, and change over time, especially in real South African conditions where buildings are often constructed in stages and used in ways that evolve. When steel is placed properly, cracks are usually controlled. When it's missing or misplaced, cracks are only the beginning. So the next time you drive past a site and see steel everywhere, you'll know exactly what it's doing. It's not making the concrete stronger, it's making the structure smarter. Hi everyone, the South African engineer here. If this explanation was useful, please like the video, subscribe, and turn on your notifications. Every subscription is a brick used to build the Engineering Explained house. Let's build this house together. Thank you for watching.